Hey guys, this is me solving a couple of the problems on your homework that I gave you. This is directly pulled from the equilibrium constants worksheet that you have to do. This problem is problem number 1A, and then we're also going to be solving problem number 3. Now, bear with me because, again, with the software I have at home, it's not the easiest to actually record myself doing this, nor do I have the best handwriting in general, but much less drawing with a mouse on a computer screen. So I'll try to make it as legible as possible. I know you guys are going to comment and talk crap about my crappy handwriting, but that's okay. I encourage it. It's fine. But let's get started. So the first one, problem number 1, is asking us to write an equilibrium expression. So if you recall from my notes, I told you equilibrium expressions require no math whatsoever. You're not actually solving for the equilibrium constant. You are just writing a roadmap for if you did have to solve for the equilibrium constant like it would ask you to do in problem number 3 down here. But for right now, we're not doing that. But the first thing you have to do when looking at any of these is you have to take stock of your actual chemical equation. Is it balanced? And we have to check those things. Well, there's 4 oxygens on the left side, there's 4 oxygens on the right side, 1 nitrogen on the left, 1 nitrogen on the right, which means yes, it is balanced. We do not have to add any coefficients, which is awesome because less work for us. Then, to begin writing an equilibrium expression, well, the first thing you really have to do is you have to write KEQ equals. Cool, because this is you telling me I know what I am doing. I would be solving for KEQ, and we're writing the expression to do so. On the right-hand side, we have this super cool little fraction bar. If you recall from my notes, products are going to go on the top, reactants are going to go down below. So hopefully by this point you know that everything on the right-hand side is a product and everything on the left-hand side is a reactant. Hopefully you know that by now. I would expect that of you. Then we draw my super great messy brackets on the top just to kind of set ourselves up. I know they don't really look like brackets, that's okay. And we start filling stuff in. Our 2 products are oxygen and nitrogen dioxide. So all you have to do to write the expression is you have to write O2 and NO2. But one thing that I would like you to pay attention to is this absence of coefficients here and here. If we had had coefficients, we would have put them as exponents, but since we don't have any, we don't need that. Our next step is to fill in our reactants. Again, we're going to trace some brackets down here. And we just fill in our reactants. In this case, we have O3 and we have nitrogen monoxide. Again, you do not have any coefficients up here and up here, so you're not going to have any exponents down here. And that is it. That's all that you need to do to write that equilibrium expression. Super easy, barely an inconvenience. Down here for number 3, on the other hand, this is where you start getting more information, some of which you are going to use and some of which you are not going to use. So your job is to really sort through this problem and figure out what information you need. So reading it aloud, at 1,000, this is supposed to be a degrees, it's supposed to be degrees Celsius up here, not down here. But at 1,000 degrees Celsius, a 1-liter container has an equilibrium mixture consisting of 0.102 moles of ammonia, 1.03 moles of nitrogen, and 1.62 moles of hydrogen. And then, I don't know why it didn't copy in here, but this is supposed to say calculate the KEQ for the equilibrium system. And here is your reaction. So this problem was really nice, and it told you what reaction was going on. Now, we're definitely going to use this. This is crucial to writing equilibrium expressions and then solving for KEQ. The temperature, though, you don't need that information at all. Not for what I'm asking you to do. There is no point in an equilibrium expression where you would plug in temperature. So to make this easier, I'm going to cross that out for us because we don't need that information. So why let it distract you further? We are in a 1-liter container, which is actually useful for this problem because it didn't give you concentration. It did not give you moles per liter. It gave you how many moles. But it told you that that many moles are in 1 liter. And if you remember that molarity equals moles per liter, that's important to know because this amount of moles becomes your molarity and therefore becomes your concentration that you're going to plug in. So step 1, we're going to write our equilibrium expression because that's always step 1 for these type of problems, just like we did up before. We have our products on the right, our reactants on the left, therefore products go on top, reactants go on the bottom. In this case, we only have one product. We have our NH3. And in this case, this reaction right here, which is balanced, by the way, and you feel free to check that yourself if you're not sure, but this does have a coefficient right here. So we're going to put an exponent up top in our equilibrium expression, our expression that we need to solve the problem. We again have two reactants just like above, so we put them down there. We have our N2. There is no coefficient by our N2, so we don't have to put one in here, and we have our H2, but we do have a coefficient, so we need to actually put that 3 in right there. Not 3 comes from up here, just in case you weren't sure. Now, we've done the groundwork. We know where we need to put our numbers. So we now can start filling them in. And wow, I'm going to undo that. That was a horrible line. Let me find the undo button. That was bad. That's a little better. So now we actually start to plug in our numbers from this problem up here. So our concentration of NH3, well, the concentration of NH3 or ammonia is not directly given to us. It's given to us in moles. But again, moles per liter is molarity. So this 0.102 becomes our concentration. So in our brackets, we put 0.102, and we have to raise that to the second power. Then, on the bottom, we're going to put our N2 concentration, which again is the same as the number of moles, in this case, our 1.03, just like this. And we have to put our 1.62 moles of hydrogen, 1.62, and we're going to raise that to the third power, just like they did, or just like is indicated to you in the problem. So we now need to do a little bit of calculator work, which I'm not going to bore you with me typing in numbers, so I did it ahead of time. But when all is said and done, you end up, or you should end up, if this is a miscalculation, please somebody feel free to correct me in the comments. I will post a video correcting it in the future. But I got 0.00238 for my KEQ, for my equilibrium constant. Now, you could have written this 2.38 times 10 to the negative 3. You could have written 0.0024. That's fine too. But I will tell you that a lot of times KEQs don't have units at all. They do not have units because really you're just figuring out the ratio of concentration to concentration. So even if you did try to put the molarity units in there, they would cancel out ultimately. So even though this problem does not ask it of us, we're going to analyze this KEQ really quickly because why not? And you're listening anyway. So you guys can obviously tell me that this KEQ is less than 1. So if you recall from my notes, KEQs that are less than 1 mean that the reactants are favored and not the products. And that mathematically makes sense because there is more down here. There's a higher concentration of these guys down here than there is up here with this 0.102 up here, and squared it's even smaller. So when you see this happening, it means that the backwards reaction is favored, and at equilibrium there is going to be more reactants, more of the N2 and the H2 than there will be of ammonia. So if I ever asked you, based on your KEQ, what does that tell you about the reaction? That's what you would tell me. You would tell me which reaction is favored, the forward or the reverse, and you would tell me at equilibrium, what am I going to find? A higher concentration of reactants or a higher concentration of products. So I hope that was helpful. I'm sorry about my super bad handwriting on a mouse, but again, I'm sure you can figure it out. It's legible at the very least. Have a good day. Email me if you have questions. Stay safe. Bye.